Hello, everybody. Thank you for being here. So we're going to start this session with three very interesting speakers. And the first one is here. He's Jim Scarletta. He's an engineer from wolfSSL. He has nearly 40 years of professional experience in both government and private industries. He has been working with wolfSSL for the last few years, developing embedded solutions mainly. And he's here to present you how to ensure firmware integrity and authenticity with wolfBoot. It's a quantum-resistant secure boot for aerospace embedded systems. So please welcome Jim Scarletta.
Microphone working? Yeah. Yeah, so I'm here today to talk about ensuring firmware integrity and authenticity. And so the objective of some of the things that I'll discuss today, we'll talk a little bit about wolfSSL and specifically about wolfBoot, the bootloader. We'll talk about conventional secure bootloaders and what the threat model might be. And we'll talk a little bit more about post-quantum and some of the importance of using post-quantum these days and what some of the deadlines are, and some solutions in the road ahead. So first, a little bit about wolfSSL. It's a C-based library, often used for embedded systems. It's got a really tiny footprint. It's dual licensed, got 7x24 support. A lot of you guys here are probably specifically in the satellite industry. As a vertical company, wolfSSL is a horizontal company across a variety of different industries. So aviation, medical, automotive. So wolfSSL has been around for about 20 years. It started out as part of MySQL, had a name change over the course of years. The important thing is here, there's no external dependencies. Nothing else has been brought in from another third party. All the solutions have been developed in-house by the same staff of engineers following the same best practices. We have three main areas of focus. So the first one being, of course, just data at rest, a file on your computer, the data in transit that you'll use something like a TLS or DTLS 1.3 to transmit a file. And the third one is our firmware updates, and that's specifically what I'll be talking about today. And so data in transit, some of the risks to non-post-quantum cryptography is where somebody will gather up a bunch of the data that's in transit with the hopes of being able to later decrypt it, maybe to later figure out your private key. And the other thing is with firmware updates, where you can fraudulently sign an image and forge it later. And so here's some of the different products provided by wolfSSL. The main core library is called wolfSSL. The cryptographic engine is in wolfcrypt here. That's where all the different libraries are stored. We're specifically talking about wolfBoot here, so this one here. And wolfBoot works really quite well with the HSM and TPM modules that we'll talk about in a little bit more detail. To use the same wolfcrypt libraries in other languages, there are wrappers for Java, C#, and Python, some of the ones you see across the bottom there. So it's all open source, so there's nothing proprietary. You can go out to GitHub today. There are a bunch of examples. You can download it, take it for a test drive. It's GPL v2 licensed, so if you follow GPL v2, you can use it for free. If you want a closed source solution, there are commercial licenses available, and you get professional support to help you migrate. A lot of people come to us wanting to migrate away from OpenSL as a better solution using wolfcrypt. And so specifically today, we're going to talk about wolfBoot as a secure bootloader. It's been around for a few years now. It runs on a variety of different microcontrollers and microprocessors. So it's got some unique features. I don't know, a quick show of hands, developers in the audience. So a few developers. So Delta updates, so if you want to send just a little bit, you don't have a lot of bandwidth to a satellite, you want to send just a small update, we support that. TPM integration, trusted platform module. If you want to have something other than your public key, just store it out in the open in read-only flash. And so here's a typical secure boot system. In the case of a satellite, the embedded system might be hundreds of miles up in the sky. The trusted source would be the ground station. And the objective, of course, is to take a trusted source and run it on the embedded system and prevent an adversary from running the software. And so the specifications, some people have proprietary solutions out there. So wolfBoot follows all of the RFC, the best practices. In the case of bootloader, RFC 9019. So here are some of the more details. Some of the interesting things are, of course, like the HSM for storing secrets, to be able to, like, signing the manifest. So you have an image you want to send to a satellite. You want to sign it. The bootloader there will check to make sure it's valid. And we rely on a trust anchor, and I'll show you. There'll be a couple more slides that will go into more detail on the importance of the trust anchor. And so again, here we have the secure boot, right? You have an embedded system manufacturer with trusted firmware that you want to run on the embedded system. And this, pay attention to this. This is where the bootloader runs right there on that cylinder. And so what you want to make sure is that if somebody else has what looks like trusted firmware that sends it to the embedded system, it could be different. The results could be catastrophic, just bricking a satellite, or it could be just something really subtly different, right? Maybe in addition to sending some data over here, it sends it on a different channel over there. And so I gave a presentation last year at Hackaday specifically on repurposing commercial products, where you would take firmware and you'd have a commercial product and you want to put your own custom, perhaps open source software on it. And I have, if you're interested in that, across the bottom there, I have the slides available. And so I used open source hardware. I used this tool called a TieGuard. It's a JTAG debugger. It's something for software engineers and hackers. Specifically, this allows you to force firmware onto a device that maybe it hadn't expected, and also allows you to read firmware. A couple of years back, there was a competition here at CYSAT, and there were some hackers invited to hack into a satellite. And although these are in French, it says, yes, they were successful. Anybody can do it these days. So a couple of years back, I bought myself some equipment, and this is the very first image I pulled of our planet from a GOES 17 satellite from my backyard. I have a blog at the bottom there that goes into details on how I did that. You can buy the hardware really inexpensive. So for under a couple $100, I bought this antenna. And I didn't transmit, but the transmit technology exists today. Phased array technology, that's what SpaceX is using, allows a really inexpensive and low power backyard antenna to transmit to a satellite. And so, I mean, the point is, if I can do this in my backyard, just imagine what a nation state might be able to do with unlimited resources. So for the folks that are not developers in the audience, I really want to emphasize there are tools available. You know, a lot of times technical people come up on the stage and talk about things in abstract terms. There are tools available to let you see in plain text what's going on. And in this specific one, this is Wireshark, and you can see that I'm doing a post-quantum key exchange. For the developers, it's super easy. You have an SSL, a secure socket layer connection. Here I am turning on post-quantum. And I'm presenting all this as information, not as fear. We have proven secure bootloaders that can help address some of these issues. For post-quantum cryptography, for all of the threats against some of the conventional cryptography algorithms, there are a variety of post-quantum available. So, and in particular, this third one here, focusing on a layered defense, right? There's no single solution to ensuring the security of communications and embedded systems. And the last one here is always using standards-based over black box solutions, right? It's super important that everybody can see and evaluate and test, because if you have a black box, you don't know that it's going to be secure. And so back to the example of sending an embedded image. So here we see the trusted firmware. Whoops. Here we see the trusted firmware. Here, can you guys see that, the yellow, the green there? So the trusted firmware here, we follow RFC 9019. It runs here on the bootloader, and basically it's signed at the embedded system manufacturer, signed with a private key, checked into the embedded system with wolfBoot to make sure with the public key that it's valid. So in the assumption with conventional cryptography is we assume that the private key cannot be derived from the public key. I mean, it's the public key, right? Well, yeah, that's something we're going to revisit with post-quantum. And so specifically with wolfBoot, we'll talk about some of the things that are new. I mentioned a variety of microcontroller devices are supported, all the embedded systems. It's super easy. It's been written to be super portable to new platforms. And there are CPU-based systems, so like all the desktop systems. So perhaps you have a satellite with an embedded device and you have a ground control station that you want to run only authorized software. There's also a wolfBoot for that. And so here we see secure boot, some of the details on a microcontroller. For the developers, the fact that it has a really small footprint is super important, and some of the different partition mechanisms for updating the image. So if there's, for the ARM developers, there's a specific type of hardware. Of a secure domain, wolfBoot is fully supported for the ARM architectures in the trust zone M. And for microprocessors, right, the microprocessors that might be in your PC, the boot loading process is considerably more complex, and we support all of the different mechanisms by loading the initial boot image. And so, for instance, here's an example of what's going on with the Intel Tiger Lake. You see there's many more steps in booting on your PC. So the boot strategies, we also support the A-B approach, where some systems allow you to run code from one of two different locations. Typically, a microcontroller allows you to only update and run from a single location. There's a single place in memory where the program will run. And in that case, we also support the boot update process, where you send an update, and then once it's validated, you move it into the single boot partition. So trust anchors are fully supported by the open source and RFC 6024. This is the important mechanism by which there are standards based on where you're going to store the public key on the device and how you're going to use it. So the trust anchor it's just what it sounds like. It's probably the single most important thing. Hardware has its own vulnerabilities as well. So there's a variety of solutions, such as a TPM, a hardware solution. Some folks just write their public key into Flash. That may or may not be a good idea. We have full support for Wolf TPM2. Hands, who knows what a TPM is? Yeah, so most people, for those that you didn't raise your hand, it's a little piece of hardware that allows you to offload some of the cryptographic functions, and so the program that's running doesn't do those operations. Some of the offloading can even validate. You could validate a software image without the running program actually ever seeing or handling the public key. The public key is stored in the TPM module, or in some cases an HSM module at manufacturing time, and the running software can potentially never even see the public key. And we'll talk a little bit more about why that might be important. And post-quantum is one of those reasons that it's important. So here are some of the features and algorithms that have been added to wolfBoot over the course of the last few years. wolfBoot was in development long before post-quantum, so these are specifically the post-quantum algorithms that were added to wolfBoot. One of the most important features is the FIPS 140-3 certificate. There's a third party that certifies that all the cryptographic algorithms are working as designed. All the microprocessors, the Intel chips. We have a really cool key store, and for the developers in the audience, there's a flexibility in changing where the key store is. So maybe you start out with something that's in Flash, and then at some point in the future you want to add a TPM. And so the libraries are designed so that the developers don't have to spend a tremendous amount of time modifying the code to go from one type of key store to another. And of course, we talked about the post-quantum secure boot, and we'll go into a little bit more detail on the hybrid. So FIPS 140-3, we're really proud that we got our certification on July 11th of last year. So that's a really important thing. It's actually required, even if you're not today doing business with the United States. If you ever plan to in the future, or you have a joint mission with the United States, the FIPS 140-3 is a requirement and will continue to be a requirement. And it's basically there's a third party that verifies the cryptographic algorithms that you've implemented are actually working as designed and intended. So we talked a little bit about the key store, right? We talked about how you might have some write-protected flash. At some point in the future, you might want to upgrade to a TPM. And so here's a visual example, a little diagram of the abstracted storage mechanism with a key store API, so that instead of having to write to the TPM module yourself, you can use the wolf TPM module to more easily just say, like, okay, here's my key, go store it. And if you want to change it from storing it in Flash to a TPM, it's just a minor configuration change. And so some of the issues on migrating to post-quantum secure boot. So of course, that's one of the things we're talking about today is specifically post-quantum. And so why don't we talk about why we would want to migrate to post-quantum? And so, well, let's say we had a sufficiently capable quantum computer. To my knowledge, we don't have one today. Their nation states might have developed one in secret. And so the question is what does that mean for your data? And there's a little TV there with a bunch of static, and it's the exercise of trying to find the key in what looks like a bunch of random bits. And so the thing with quantum computers is they can only solve certain kinds of problems. They can't solve every problem. But one of the things that supposedly they're going to be really good at is factoring, and in particular factoring the product of two large prime numbers, which is the root of how some of the cryptographic algorithms, such as how RSA works. And so, well, what does that mean? What if you can figure out, like, the product of two large prime numbers, if you can figure out what those two are, like, well, what does that mean? Well, remember we talked about giving your public key, which, yeah, right, it's public, so you should give it to anybody that you want. So a sufficiently capable quantum computer would be able to derive your private key from the public key, and you realize what a disaster that could be, right? So whatever was, you were always worried about securing your private key, and now we have a serious problem on our hands. And so what do you do? Well, we have today post-quantum cryptographic algorithms. They've been implemented at wolfSSL for quite some time now. So basically the premise here is the math, right? Your private key is not easily solved by a sufficiently capable post-quantum computer. And so there's like this module lattice-based math, affectionately known as ML-Chem, is an example of one of those new post-quantum algorithms that isn't easily solved by a post-quantum computer. And so some of you may ask, well, when will it be a threat? Well, it doesn't matter. We have post-quantum algorithms available today. For existing systems, we really should, today, be considering some sort of upgrade plan because, yeah, we have solutions today. So this was announced a couple of years back by the NSA, and they released some specific algorithms that were going to be approved. You see the big long link at the bottom there. A lot of you, probably everybody here, has probably seen this timeline of requirements. 2025, what we're talking about today, software firmware signing is required this year if you're following CNSA 2.0. So yeah, again, starting this year, like if you're going to do secure boot, we should be doing post-quantum this year. And so see, these are some of the algorithms approved by NIST. I highlighted some that are stateful and stateless. You'll see that, for instance, MLDSA is a stateless digital signature, and a digital signature is the signature that you have a firmware image and you'll sign it. So FIPS 204 specifies that MLDSA is one of the ones you can use to sign firmware. We'll talk a little bit real quick about the difference between stateful and stateless, because yeah, they're similar words. So stateful, basically that means what you need to do. You need to remember the state. And so you need to keep track of what you're doing. Stateless allows you much more flexibility without having to keep track of counters. Stateful, yeah, these are the things where you do have to keep track. If part of the key is, if the state is lost or misused, mismanaged, it can be disastrous. Stateless do not require tracking state. They're much simpler to implement and deploy and much less likely to have any human error. So back to our secure boot, we have Again, we talked about how you have some firmware, you assign it with a private key, you send it to the green cylinder there, the bootloader, checks it with the public key, and installs it if valid and runs it on the embedded system. So for a stateful post-quantum cryptography, this mechanism would not be valid. For stateless, it would be. So for MLDSA, you could do a mechanism such as this. We do have a solution, an HSM solution that manages state for you. So there's a separate software solution. It's called wolfHSM. A little piece of hardware, and the wolfHSM talks to that hardware and allows the when you're signing the software, the HSM keeps track of state for you, and it's all kept track internally, so you don't have to worry about leaking secrets. It's all done inside the HSM. And so the migration strategies. So we talked earlier about some of the risks and the immediate concerns in the migration paths, and in particular, using a hybrid secure signature scheme, right? So here we would, in addition to using a known, valid, conventional cryptographic algorithm, you can also use concurrently something post-quantum. Post-quantum, it's still kind of new, but you can use both. You can use the best of both worlds. And so here again, we saw signing an image with a private key, send it to the embedded system, and using, so wolfBoot supports dual key, so you assign it both with a private key here for post-quantum, a private key for conventional, so there's two signatures attached to the manifest. It gets sent to the embedded system, and there's two public keys. And so in conclusion, wolfSSL, it's more than just a universal secure bootloader, so you saw the additional features. It's FIP certified, so there's, not only has WolfCrypt been certified, we have a lab that can certify your solution. Runs on a variety of targets, microprocessors, as well as microprocessors, microcontrollers and microprocessors. It's quantum ready, so we have a variety of post-quantum cryptographic algorithms available. And of course, we talked about using the hybrid, using both post-quantum and conventional. And so back to what we learned. So wolfSSL has been around for years. It's widely used. It's all on open source. It's out on GitHub for anybody to download, take it for a test drive. Companion products for things like TPM and HSM. We talked a little bit about some of the risks and mitigation, like what it means to sign firmware, stateful versus stateless, why post-quantum is important, some of the solutions available. And the road ahead, I really want to emphasize the importance of open source. It's super dangerous to have a closed source solution where nobody can see what's inside. So everything at wolfSSL is open source, available for anybody to evaluate. And of course, collaboration. I'm glad everybody comes to a conference like this and compares notes. And so that's my presentation.
Thank you, Jim. Thank you. So now if you have any questions, I'll leave the microphone.
So thank you for the presentation. When we talk about embedded systems, do we need to consider the differences between post-quantum in performance, actually the differences in performance between post-quantum crypto and traditional crypto?
Told me to talk into the microphone. Yes, the post-quantum algorithms are on par, a little bit slower by just a little bit, but that's a valid question. It's depending on your system, it's probably negligible, and we do have some performance enhancements. We've typically seen maybe half the speed. But if there's a problem with performance, we can certainly work with you on that. But it's on par. But that's a good question. It's not significantly more, and so yeah, I don't think that should be a problem.
And maybe I have a question related to that. I've seen on your website that you are working also with Cortex M0, so very small MCUs. Are there some hardware limitations for the post-quantum solutions? Do you require TPM, etc.? What are the minimum requirements?
So there are all of the libraries are software-based. We do take advantage of hardware acceleration when available on a chip. We do take advantage of a TPM or an HSM, but none of them are required. So if you have an embedded system with no special hardware, there's no special. Was that basically the question? Was like anything?
Yeah, and the minimum requirement because of the Cortex M0.
Really, the only limitation is a moderate amount of RAM. You probably wouldn't want to do it on a 2K Arduino, but it should run on pretty much any platform with no special requirements. Yeah.
Okay, including post-quantum algorithms.
The post-quantum algorithms should run anywhere. I myself have run them on relatively minimal, tiny microcontrollers. Yeah.
Okay.
Other questions?
Any other questions? Yeah. Thank you for the presentation. I was wondering if wolfSSL is considering implementing also Falcon.
Falcon, we've talked about it. I personally don't know the answer to that, but see me after. I can get you in touch with the guy that's doing our post-quantum stuff. I remember talking to him about Falcon. Don't know what happened with it. That didn't end up being one of the final approved algorithms, did it?
It will receive its FIPS.
It will? So
eventually.
I can get you in touch with our post-quantum guy and can answer the Falcon question.
Thank you.
Sorry.
Hello, my question is similar to the previous one. It has to do with the new post-quantum algorithm from the NIST competition is the HQC algorithm that is going to be standardized in 1 year, more or less. So
and it's called what?
It's HQC. It's not based in lattices. It's based on a different mathematical problem.
Yeah, that's another good question. See me afterwards. Same answer. I can get you in touch with our post-quantum expert. I don't know the answer to the HUC.
HQC.
HQ. No,
Coming quasi-cycle, maybe. I was. Let me check. Yes, Hamming quasi-cyclic.
Not familiar with that, but I can get you in touch with somebody that will know.
Okay.
Right. Sorry.
Thank you.
Thank you.
Any other questions? Okay, we have 2 questions from the chat. So this is the first one. Do you recommend switching completely to post-quantum?
Well, that's an interesting question. Me personally, I would say no. So post-quantum has been around for a relatively short amount of time. There isn't a sufficiently capable post-quantum computer today. And I would still recommend doing the hybrid with both conventional and post-quantum. Ask me again in a few years when all the really smart people out there test the post-quantum safe algorithms, when there's a longer track record. wolfSSL might have a different, so that's kind of my personal view. I don't think you should switch completely to post-quantum. I do think you should use a hybrid solution.
And just one last question. Do you know if the presentation will be available somewhere? It's a question online.
I thought you guys were recording it, but my slides are available. If you want to send a message to fax at wolfSSL, I can certainly share my slides.
Great. Yes. So I think you also will have the video, but if you want the slides.
Oh yeah. So fax, FACTS at wolfSSL.com, and I'm happy to share my slides with anyone that's interested. Happy to talk with anyone that's interested.
Great. If you don't have any questions, thank you very much for your presentation. Thank you very much.